This is the recap. We did quantum mechanics, and we looked at a lot of the properties that they discovered in quantum mechanics. We have superposition. What is superposition? Well, superposition is a horse gallops and stands still at the same time. Okay, so how they manage that, we don't know, but they say the particle vibrates and it doesn't vibrate at the same time.
That's when you're really sleepy but drink a lot of coffee, isn't it?
Schrodinger's cat, you got to peek inside the box. Otherwise, the cat, meanwhile, is both dead and alive.
And that was an analogy for what?
That's Schrodinger invented this. Erwin Schrodinger, he invented this analogy to explain what these people, the people from the Copenhagen interpretation, which was primarily Niels Bohr and Werner Heisenberg, what they were saying is, he was saying, this is what these guys are saying about the microscopic world, about the subatomic world. That it's like if you have a cat, the cat is both dead and alive until you peek. And that's why we have that, the all-seeing eye there. You got to look inside the box to find out if it's dead or alive. At that point, as soon as you look, as soon as you interfere with the experiment, at that point it collapses to either dead or alive. But meanwhile, it's in both states.
I'm sure the spiritualists had a field day with this one. Consciousness changes matter, essentially.
That's why these people talk about consciousness lately a lot, because they eventually end up getting out of physics and talking about
that's what this is, essentially. They're saying with consciousness, with an eye, with a witness, we're changing reality. Just by having an eye on something, the cat is either alive or dead.
Yeah, and the issue here is that they put the observer at the center of the whole process. Yeah. So if the guy's drunk or is on high, we got to rely on his testimony. Okay, then we go into spin. What is spin? Well, the spin is also more or less, they have all these dualities, and in the case of spin, the dancer spins clockwise and counterclockwise at the same time. Again, it's all these dualities that they have.
What was this in relation to?
They say all particles spin, but they have all these dual spins until you put your measuring device there, and then it collapses to either clockwise or counterclockwise. And again, spin is not spin. There, these two dancers are spinning. That's not what these people are talking about. When they say spin, they're talking about something completely different, and it's got to do with orientation. It's like at that point, what they're looking at is
if you put a line on the ball, depending on when you look, the line is pointing in a different direction, and that's how you could tell by how much time passed, how much it turned,
what they're saying is, imagine this is, you can explain it very well with a rope. In fact, let's do it here. We're going to do this experiment. It's a very dangerous experiment. Put your hand crosswise, like cutting it, So that, that's okay. Okay, so it's like that. So show the screen now. Okay, so he cut it there. Okay, so that's what he gets. He gets that cross section right there. Okay, now if you move a little, then it changes. It changes the curvature.
Circles, I guess where the two circles are, right?
Right. Essentially, with a rope, you can explain what these people think about as spin, because what they're doing is doing a cross section at a given point. See, the way they measure these things is with an ellipsometer, or something comparable to an ellipsometer, which is what I use in the industry. And that is, at some point where you have the detector, at that point, it's the cross section of light. Whatever light's going there, it's like you're cutting light. If you have a laser going through there, it cuts the laser at that point. And at that point, it's got a given orientation. They say, oh, that's spin. It's spin 1. That's when spin half. This one is spin -1. That's what they call these things. And all you're doing is, if you move along that line, that rope, you'll find different orientations of the rope. That's more or less what these people call spin. That's the best thing that I can give you as far as what spin means to them. It's a static concept, not a dynamic one like a spinning top. That's my point. Okay, from there we move to tunneling, and tunneling looks like this. You have the snowball, and it goes through the mountain, but the way it does it, it turns into a wave, and then it appears on the other side. So from one side of the mountain to the other side, it goes instantaneously, because the part that goes through the mountain does it as a wave, and it appears on the other side. They call that tunneling.
Are they saying photons go from
and electrons?
Yeah, they go from a particle to a wave when it goes through something, and then back into a particle?
Essentially, that's their explanation. What they're saying is the snowball appears on the other side of the mountain instantaneously, as if the mountain weren't there. So there's distance, but there's no mountain.
But what's the snowball talking about exactly?
Well, the snowballs, it could be photons or it could be electrons. So think of a snowball as an electron. So they're saying this electron...
the mountain is what?
Is a barrier, an energy barrier.
What do you mean by energy? Like a break?
Not quite. It's mathematics. It's just an energy barrier, and it turns out it's a barrier that's sufficient to prevent the electron from going through. And the electron does go through, but it goes instantaneously through the entire barrier, through the entire energy barrier, as if the barrier weren't there. So they say it goes through there faster than the speed of light.
Yeah.
And the only way they can explain it is they say, well, somehow it stretches its neck across the mountain and it appears on the other side.
How did they figure this out?
Or
when did they just calculate this?
No, yeah, it's
Is this an experiment or a calculation?
This is a calculation performed on an experiment. They have to answer the experiment, and they say, we see it on the other side. We don't know why, but this is the calculation. And from the calculation comes the theory, and the theory is that somehow the particle appears on the other side, which is so far a description, and the way they try to get around it is saying, well, remember that an electron, just like a photon, is not only a particle, it's also a wave.
Oh, yeah, that's just cheating.
Yeah. So they turned it
But
into a wave.
Experiment? What was the experiment?
Well, they've got several experiments where they verified this behavior, okay, where they have this energy barrier, and they have the electron, and they have electricity, right, flowing through there, and there's this energy barrier, and somehow electricity
I don't
gets
like
through
the word energy barrier.
Yeah, well, I know, but
Both
there's
of
no other way
words
to...
are question mark. What do you mean? What is actually going through there?
I had to put the mountain because people understand mountain. People don't understand an energy barrier, okay, so...
because it doesn't mean anything.
I know, it's a mathematical concept, and they're saying there's this energy, this wall of energy, whatever you want to think of it as. I put it on a mountain so that you can understand physically what's going on, and they're saying that this electricity is going through there. They put this energy barrier, and the electricity, under certain circumstances, goes right through, and the only way they can explain how that electron, because electricity is the flow of electrons, how it got through that energy barrier is by turning it into a wave that stretches its neck across, and they say, oh, see, that's how it ended instantaneously on the other side of the energy barrier. And so the only way I can illustrate that is with a mountain and saying, the snowball went through the mountain as a wave, and that's how it appears on the other side. That's it. Take it or leave it. Okay.
They like invoking magic, don't they?
Yeah, they do. Okay, and then moving on here, we have the Mossbauer effect is the other one, and that's recoilless emission. Okay, and what is that about? Well, Mossbauer said, when you have the atom is in a lattice, like in a crystal lattice, and it shoots these gamma rays out there, it's got to be with high frequency gamma rays. There's no recoiling, or none that they can measure, which is probably a better way of putting that, none that they can measure, and they say there's essentially recoilless emission. And the folks at the Harvard Tower experiment, they use that unknown, that phenomena, that observation that they cannot explain. They use it for the Harvard Tower experiment where they showed that gravity pulls on light, okay? Which is, they didn't get it over, this guy did, okay? And all I'm saying on that is that this is what Mossbauer was really looking at without knowing. He's got a rope tied to that atom, and again, if it's a bigger atom than a hydrogen, we're going to have many ropes, okay?
It's basically the same picture, same GIF.
It's the same thing. What we have is that there is no such thing as a wave. Okay, wave is a verb. You got to identify the thing that is waving, and that's where Mossbauer failed as well. Like all others, because they don't have a physical entity in there. Okay?
They didn't have a good foundation.
Yeah, all they have is math. All they have is just all this math, and they try to get it away with just a what they say is a physical interpretation. When you put them against the wall, and they say we don't understand it either. And anyways, that's philosophy anyways.
Well, I've often
why did they try in the first place?
I've often wondered if you can apply math to the rope model. Like if you could calculate the torsion of a rope, if it would fit the exact.
The equations are all out there. You look for equations for torsion. It's all been done. So I don't do math. I did a lot of math when I was in college, but I don't care about math. But those people who want to know how fast or all that stuff, they can calculate all that stuff by going to the equations for torsion, and they're all out there. And you can calculate the speed of light. You can figure out what the torsion is on the rope. Okay, if you're interested, go ahead and look up.
Get a Nobel for that.
Yeah, you might get a Nobel. You never know.
Hey guys, I proved the rope hypothesis stuff.
Yeah, here's
get out of here.
Okay, ray reversibility, next one on the line. What was that all about? Well, I put that in my real physics cartoons there, and essentially light retraces its exact path. That's why you see yourself. Every piece of your body is mirrored in the mirror. Okay, and when you send light through a lens, light goes right through the lens, coming back along the same lines. How do you explain this?
That's a really nice GIF. I like the top right one.
Yeah, how do you explain this with particles? I mean, don't they get lost? You would think they do, right? And so this is the lunar ranging experiment that you could say the same thing here. How do they do this with the lunar ranging experiment if light travels exactly in a straight line? Well, it turns out that they have to shoot the light in front of where the moon is going to be in 1 second, because The moon is 1.25 light seconds away from us, like 300,000, a little more, 380, I think it is, 380,000 kilometers away. That means light takes 1.25 seconds to get there, and to come back, it's 2.5 seconds. What does that mean? It means that in order to do this, light has to travel completely straight, because that's what the ray reversibility says it does. And what these people do is they say they shoot the laser where the moon is going to be in 1 second. And remember that in 1 second, the Earth moves 30 kilometers around the sun, and the moon moves 1 kilometer around the Earth. That means both objects moved in space. So how is it that the photon went and came back? Well, their argument is that they send gazillions of photons out from this powerful laser, okay? And what comes back, what returns is just a handful, maybe 20 photons. That's what they detect in their computers, because they have these detectors, and they turn that into signals, and they have these peaks that they look at, and they say, okay, here's a peak that came from that laser. And I'm going to get to that in a second, because a person asked a question about that, okay? And so let me hold off on that explanation for a few seconds here. And let me get to that final one, and that's the magnetic lines of force, which I covered the other day. When you put two magnets together, their lines of force merge somehow, and lines of force go around both magnets as if it were a single magnet. That's what happens with the lines of force. We know this only because we sprinkle iron filings over them. So if you sprinkle iron filings over two magnets and get them eventually together, they act as a single magnet, and the line of force goes around both of them. Okay, and we have to explain that. What are those lines of force? Well, they never figured it out. They say those are abstract, they're not real, they're imaginary. But it turns out that these imaginary lines of force not only move iron filings, but they are called lines of force, meaning they cause forces. And how can they affect things in the real world, in our three-dimensional world, like iron filings, if they're imaginary? And so this is what they never answered. They never answered that question. Okay, and so what can I say? We don't have an answer, at least from quantum mechanics, for lines of force.
You don't know what magnetism is.
Well, so we don't know any of those things. We don't know superposition. We don't know spin. We don't know lines of force, ray reversibility. We don't know nothing from quantum. The mathematical physicists don't know nothing.
There's a lot of Nobels to be had.
Yeah, and so
we just need to find more particles.
In fact, we had 120 years of Nobel Prizes, and we have so much ignorance. And they say, well, we're still investigating. What are you investigating? I mean, this is an issue of identifying the invisible actors. That's all it is. Once you identify the invisible actors, all this is kindergarten stuff. And I'm saying exactly that. Kindergarten, it's kid stuff.
Even then, it isn't, though.
It is, because it's what I say. If you see a guy pulling on a box, and the box goes up, and you don't see anything else, you say, oh, he did that by magic. It turns out that, you didn't see the rope that's tied around the invisible pulley. But if I show you the pulley and the rope that's tied to the box, and that guy's pulling on the rope through the pulley, they say, oh, anybody can understand that. I see everything there.
Yeah, but how many motions does Adam have?
But only because you cannot see the rope and the pulley, you think the box went up by magic, and you say, how can it do that? And all you do is describe mathematically, saying, well, the box has so much weight, and it went up at such and such speed, and that's all these people do. No, I want you to identify the rope and the pulley in quantum mechanics. That's what we need. And that's what's never been done in 120 years.
Okay. But how many motions does an atom have? Oh, we'll hit the...
okay. It vibrates.
It's not kindergarten stuff.
Okay, and that's
you put them all together. You got a vibrating, pumping, moving back and forth, sliding on an abacus. The shell of the atom slithering around. You got a lot of things going on. You got the magnetism line. There's a lot of motions there.
Okay, that's true. But at the same time, if you were able to see it all, you would say, okay, I see what's happening here. What light is? It's a torsion of a rope.
If you saw an engine moving, there's a lot of motion still.
No, but just look
even if you see it all, it's still pretty hard.
Okay, but let's look at the simple stuff. Let's just look at light.
Yeah.
And I'm saying, look, light is a torsion. And if you were able to have the eyes of God, of the devil, of Mother Nature, Father Universe, one of those guys, and you would see the rope just twirling, and you would stare at it for a while and say, okay, I understand what light is. Light is just a torsion along this object. It would be no mystery. It's because we cannot see the mediator of light. People say, oh, what is light? Let's measure to see the speed. Oh, it must have been a particle that went from here to there. No, if it's a torsion and you see the rope and you see it all there, you would say, oh, so stupid of me believing it was a particle or a wave, transverse wave, moving up. And no, once you see the rope, you say, oh, okay, that's so stupid, so simple. And yeah, there are other motions that you got to account for, of course. Okay, here's attraction and repulsion. Okay. Okay, and the top one is attraction, the bottom one is repulsion. And no, they're not. If you look, one is going clockwise. The two on the top are going counterclockwise, okay? So you got to look at the atoms there, and you can see that they're both going counterclockwise. They're both going this way, see? Okay. And then the one on the bottom, we've turned the first one around. It's going clockwise. Yeah. Okay, so if you look at that very closely, you see the line, what I call serpentine, a line of merged electron shells. And the ones at the bottom, they're moving in contrary directions. Okay, they're moving like this. The ones on the top, they're moving both in the same direction. So it's those lines of force, the threads, right, that move and connect with the lines of force of the other serpentine. This could be two wires, this could be two magnets, it doesn't matter. But the point is that it's something physical there that we can't see or touch, something very tenuous. Okay, if we could see a thread that makes up the rope, you'd be surprised how small, how thin it is, okay? But this is essentially the mechanism I'm proposing, and at least you can understand it. Whether you believe in it or not, it's a separate issue. But the point is, here you have an understanding of attraction and repulsion.
The first one being conveyor belt, the second one being like dryer, squeezer.
Well, yeah, it's like I say, two rollers of a washing machine of the old days. When you put your shirt between them, the two rollers went in the in opposite directions, right? And squeeze the shirt through there. That's what the bottom
it's like a dough maker. They also have that.
Yeah, they've used it for different things out there,
But it's easier to give them names, like again, the conveyor belt versus dough.
Okay, I call it the what is it, the machine dryer, the dryer of the old days, right? Two rollers drying the shirt. Okay, so someone asked out there, okay, said, you want to read it maybe?
In your green animation of lines of force rotating at approximately 2758,
yeah, that's
the time. Okay. Why are the lines of force not drawn connected each to every other? Okay, I see. I would have expected each green ball to have a line of force to every other green ball. Why would the lines of force look like they do with the iron filings and not in any other way as explained by your rope model? Yeah, you simplified it.
Yeah, essentially this should be very simple. I'm saying that these lines of force are really the trajectories of the threads that are spinning around. They're spinning around because the merged electron shells of different atoms are also spinning around. They're aligned, spinning around, and swinging these threads around. That's what creates the lines, these lines of force that compel iron filings to align along the lines of force. That's all it is. They're sweeping right through them. So the threads are not connected to threads. The threads are connected to the atoms.
I was talking about why isn't there a line of force between each two green balls? Isn't the simple answer that you simplified it?
Yeah,
you didn't draw a line between each two green balls because
you
could. That's technically true.
Yeah, you can't draw the gazillions of threads there. You want to understand the mechanism. The mechanism. That's
I think that's just what wasn't clear.
Yeah,
you simplified it.
The mechanism is that you have merged electron shells of, say, iron, okay? And iron's a complex atom to begin with. I've shown pictures of iron in the past. And they merge. The electron shells merge.
They overlap.
Yeah, and what happens is they blend, okay? And what happens is they're aligned, and now they're going to spin if it's magnetized. If it's magnetized, they're going to spin. If it's not, if it's just standard iron, it's not going to spin, okay? And so if they're spinning, when they spin, they swing around the threads. Not only that interconnect the atoms, but also that form the electron shells. They come out and they form these walls of threads that swing around. And when you have two of these from one magnet and another, one live wire and another live wire, these threads are the ones that interact with each other. If they're moving in the same direction, one pulls on the other. If they're moving in opposite direction, they
slap each other.
Yeah, they slap each other and push each other away, and that's the repulsion. Those are the mechanisms. You have to use your imagination. You can even draw it yourself. I did quite a few videos on this. You can look them up. But you can draw them yourself to try to visualize what I'm explaining. Do you believe it? That's a separate issue. I'm saying I can explain to you how a magnet attracts and how a magnet repels another. Okay, through this mechanism. That's all I'm saying. And what is the magnet when you turn it around? Obviously, you're going to change from clockwise to counterclockwise, and now you're going to either repulse or attract. So the mechanism right there, and that gives me at least confidence that that's probably how Mother Nature's doing it. Okay, but you don't have to agree with me, but at least understand the mechanism. Okay, and along the same lines, because we talked about that the other day, it went all the way to the bottom. Always does that to me. And he asked the following. Let me put it over here, and I guess
the electrostatic lines of force are really lines. The magnetic are not lines, but loops. They are closed in itself. The electrostatic are not.
Yeah, what the fellow is saying is that magnets have these lines, these magnetic lines, and they're loops. Whereas the electric lines, they say, they stretch straight out of the charge. This is what the guy is referring to. So he's saying magnetic lines are not the same thing as electric lines. This is what he's saying. Okay, I'll address that in a second. Just keep reading there.
In the case of a current carrying wire, the magnetic lines are not connected to anything but in itself. How this fit with your atom-to-atom connection threads? I guess threads.
Yeah.
Don't forget that electrified wires are not equal solid magnets. Please note the pattern.
Yeah, this is what he's saying. He's saying that magnetic and electric are not the same.
It's the same effect but different causes.
Yeah, well, he's saying that they're not even the same effect. He's saying they're different. He's saying this, essentially. Here's the repulsion pattern, and he's saying those circles that you see there, he's saying that those are not attached to anything. Okay, you can see the circles. They're going around. They're not touching the wire. They're going around the wire. So he's saying those circles, those hula hoops, those rings are standalone. Well, if they're standalone, why can't you bring a ring to the conference room, to the next conference? Okay,
if it's true. They're independent from the wire.
They can't be independent from the wire, because then you would be able to have a magnetic lines without the magnet. Yeah. You would get rid of the magnet and you would have a field.
You never have just the magnetic field. It's always the effect of some cause.
Right. This fella thinks that these lines of force that make up the magnetic lines of force, he thinks they're hula hoops. That he thinks they're rings that he can pull them out, and they're not tied to anything. They're standalone.
Well, that's how they're always drawn.
Yeah, but they're not. They have to be tied to something, because otherwise you would be able to have a magnetic field, which is made of all these rings, without the magnet, without the live wire. You could have it without that, and you can't. You need something material in order to have a magnetic field, in order to have magnetic lines of force. So this notion that you have that they're rings is what's irrational. Okay, so let's look at that. Let's look at it in more detail here. This is all saying, look, here we have the rings on the top, and they have magnets. So let's get rid of the magnet that's troubling him, that's bothering him, so that it doesn't interfere with his understanding. We get rid of the magnet. This fellow is saying that that ring, okay, is going around without the magnet. He can have the rings without a magnet. That they're standard. They're not tied to anything, he's saying. Okay? Essentially, this is what I showed earlier. Okay? And you can see there that he's saying that those lines of force that are around the magnet, which are now around two magnets for some reason, he's saying those are rings that stand alone. Okay? That's his argument. And so let's look at this. Let's show him that why he is not wrong. He's irrational. Okay, here we see it side by side, so you can see it. Okay, so let's look at it in close up here. We're saying that what you're seeing there on the magnet is the same thing that you see in two live wires, which he said are different. He's saying, look, at the patterns are different. No, they're exactly the same. The one on the left, the one with the lines, that's a magnet. And the one on the right, those two on the bottom there, on the bottom right, those two are two live wires. That's electricity going through two live wires. And what's happening, they're conducting current in opposite directions. Okay, and again, you see the pattern of squeezing water out of a shirt. You know, the how we used to dry in the old days, the two rollers. And that's what you're seeing. The two rollers are working in opposite direction. One is going clockwise, the other one counterclockwise. And what they're doing, they're squeezing everything between them. Okay, that's what's happening there. And that's the same thing you see in a magnet. What the magnet does when the lines go inside the magnet, they're bumping up one line of force against line of force of the bottom part. So a magnet is not divided into south and north. It's divided into top and bottom. Okay, the lines of force, or really the threads, are swinging in the top in one direction and swinging in the bottom of the magnet in the opposite direction. And what they're doing is they're squeezing in the center of the magnet, right there in the middle of the magnet. They're squeezing what you see on the right. The two rollers are going in opposite direction, essentially.
Isn't that also how they do the colliders at CERN, where they essentially have a whole bunch of these until they squeeze the particle down to exactly where they want it? Because they use magnetism.
Yeah.
Isn't it basically the roller thing, but from
the side,
from every...
Because it's a circular.
Because
exactly. It's a circular pattern around where the beam line, the main beam line.
To get that beam line in the center, essentially they use this pattern.
Exactly.
Only 360 instead of just two. They have one
all around. Yeah, they're pushing the beam inwards. Yeah. But you can see there on the top right what's happening. You see the one on the top is clockwise, the one on the bottom is counterclockwise, and what's happening there, the threads, if you put those together, the threads are going to be bumping against the ones that are from the top with the ones on the bottom, and they're going to squeeze like you see at the bottom there. You're going to squeeze anything in between them.
To the left.
The more you try to get them together, the more the lines are going to squeeze. Yeah. So what you're staring at here is not that these lines of force are circular, they're rings, they're standalone hula hoops. No, what they're doing, you have something swinging in that region, and it's pushing the iron filings together against each other. That's what it's doing. Okay, so we have a different explanation for all this than what you see out there today. And all we ask is that you try to understand it. Okay, if you understand it, fine, we're done. We've achieved our goal. Whether you believe or not, if you got a better mousetrap, be my guest. All I can do is share mine with you.
You can visualize it at least.
Yeah. Okay, here's another fellow, and he asked about the lunar arranging. Okay, and go ahead if you want.
Lunar arranging. You could have saved yourself the embarrassment of looking like an idiot if you had bothered to do some research first. Page 16, section 3.4, second paragraph in.
Yeah, no, there's a reference. Okay.
But one must intentionally...
This is quoted from that paper.
But one must intentionally point ahead of the lunar reflector to where it will be in 1.25 seconds while looking behind the current position of the reflector to where it was 1.25 seconds ago.
Yeah, and what are we saying here? We're saying that this fellow is saying, look, if I would have read that paper, I would have saved myself the trouble, okay, of saying that, as I saw a minute ago, that the laser, it has to be pointed to where the retroreflector on the moon is going to be in 1 second. And in 1 second, the Earth moved and the moon moved, both, okay? And remember the laser's coming out of the Earth, right? So that thing is moving, and we moved 30 kilometers around the sun in that 1 second. Yeah. The moon moved 1 second, 1 kilometer with respect to the Earth. So we moved 30 kilometers, the moon moved 1 kilometer with respect to us, because the moon is essentially going faster than the Earth, because you take the speed of the Earth plus the Earth, the orbit of the moon. Okay, the moon runs circles around us. Yeah. Okay, so the guy is saying, well, yeah, they do point it to where the moon is going to be in 1 second, so you should have saved yourself the trouble. Well, we got a little problem. Let me tell you what the problem is here. Let's look at this in little detail. Okay, here's the moon. Okay. And
we're going deep. Yeah, I know what the moon looks like.
Okay, but we're gonna go. The moon is 3.5 million. I put it in meters so that we all do it in meters, and we can see the relations here. Okay, it's 3.5 million, more or less. Okay, in diameter, in meters in diameter. Okay, they point the laser. Okay, to where it's approximately 6 kilometers. Okay, they do a raster. They look for it. So it's the beam out there is about 2 kilometers. Remember, this beam diverges when it comes out of the Earth. Okay,
and like they get that cone?
Yeah, it is a cone. It doesn't stay like a pinpoint. Remember, light always diverges to some degree, and even a laser diverges given enough time length. Yeah. Okay, so what happens? The laser is diverging. Remember, it comes out of this. It's a very powerful laser to be able to shine it on the moon. This is not the little laser we use at home. Okay?
Would it be bad to look into that laser?
Well, yeah. Probably.
Would you get a headache?
So the laser pointed at the moon, but look at where it's pointed. It's pointed at that little region. I don't know if you can see it in yellow. I put it in yellow. Okay, and the retroreflector. See, the region is 6.5 kilometers, 6,500 meters. And the retroreflector is 1 meter. Okay, let's understand.
So they just area of affected.
So what they're doing is they're shooting and they're saying it's somewhere in there. Yeah. And where do they point to? They point to a region they know, the crater. They look at the crater because they can see that more or less with their telescope. Okay, and they can't see the little retroreflector. But they say we're going to hit it somewhere around there. When we get a beam back, we know we hit the retroreflector. That's how it's done. Okay. Let's make sure we understand the process here of how they do the lunar arranging experiment.
The retroreflector is super small, but it's in a crater that they kind of know where it is.
Yeah.
So they bombard the area with light until they get a reflection back.
Yeah, and here you can see, just again for reference, this is all reference. Here's the Scobie and the Smith craters, and they're 40 kilometers apart, and that's the picture they took. But they take these pictures usually from like you see there on the right, the Lunar Reconnaissance Orbiter. And that's orbiting the moon. So we have an orbiter going around there, and it takes pictures. And these are the best pictures we can get from the moon today. If you do it from a telescope here on Earth, well, you can see the one on the bottom right. You see them from a little farther away, and that's a good telescope there. Okay, so it's not like you can locate these things from the Earth. I mean, you cannot see a matchbox from the Earth. Okay, and much less, I can't say much less, but you can't see the retroreflector, which is 2/3 of a meter times 1 meter, which is about 2 feet by 3 feet, a little bigger than that. You can't see that from the Earth.
They don't know where the mirror is.
They don't know,
but they know it's somewhere in that crater.
And so what they do, they shoot in that. They shoot the laser in that region in a 6.5 kilometer wide region. It's a 2 kilometer raster that scans that whole region because they can't hit it exactly. And the only reason they know they hit it is because they get some photons back. They get, according to them, they get 21 photons back. I said it right, 21 photons. That's so they send gazillions of, they send I don't know how many billions out, and they only get 21 back. That's the signal. That's how faint the signal is that is detected here on Earth, and the computer, maps that. They say, oh, we got a peak. We hit the retroreflector. That's how it's done. So they don't know what they're doing. Okay, they just get those signals, and based on that, they say, okay, how are we going to explain this? And the way they explain it is that photons, because they're using photons, are going to the moon. A lot of them get lost. Some hit the retroreflector, others hit the crater and who knows what, a rock. And those that hit the retroreflector, a lot of them come back, and only a few of those are captured by our detector here on Earth. That's their explanation. Okay? And here's the paper that this fellow referenced, Murphy's paper. We can call it Murphy's Law. Okay? And I'm just going to point to the main points here. It says, because none of the reflectors are directly visible from the ground. Okay, he says that up front. We must rely on local topographical features whose centers are well defined. We center on the reference crater. Okay, so they look at the crater and say, oh, there's the crater, so the retroreflector has to be around here. Okay, that's the way they do it. Okay, we execute a 1 arcsec, okay, which is a little less than 2 kilometers. Okay, so if you look at 2 kilometers, that's what an arcsecond is on the moon, at that distance. Okay, that's the length. Spiral raster pattern around the nominal position to pick up the signal. Okay, and when you go to the Wikipedia, it gives you a little more detail, summary essentially. At the moon's surface, the beam is about 6.5 kilometers. Okay?
4 miles.
4 miles wide. Scientists likened the task of aiming the beam to using a rifle to hit a moving dime 3 kilometers away, okay, or 1.9 miles. The reflected light is too weak to see with the human eye. No kidding. Out of 10 to the 21 photons aimed at the reflector, only 1 is received back on Earth, even under good conditions. Jeez, this is what they're doing, okay? Now, what is the problem with Murphy and his paper and these people? The first thing you have to understand is Murphy works for NASA. And this group
That's
works
the problem.
So you have the situation of the wolf guarding the sheep, okay? You have the fox guarding the hens. And so they have to produce a report because they can't just go out there, do an experiment and...
We failed.
No, not only fail, but say nothing. Yeah. They must say something. They must explain how they spent the funds. So they have to write a paper. They have to explain what they did, and that's what they try to do in their paper. They try to explain what they did. What are the problems? Here's where we arrive at the problems, and that this fella missed completely. And they're the assumptions that he operates under, okay? And these are the assumptions that Murphy and his crew, remember they're all relativists, they're all mechanics, quantum mechanics. Assumptions underlying the lunar ranging experiment. Space is equal to a physical object. They treat space as a physical object. General relativity treats it as such, even though space is nothing. Okay, so they have space-time, and they turn that into a 4-dimensional physical object. Earth weighs down the space, okay? It warps it. The moon does the same thing, okay? Light, what is light? Mediated by beads. They're thinking of particles. So they think that when they shoot the laser, they're shooting a bunch of little photons along warp space.
The rolling marbles on a...
We got the rolling marbles, okay? The beats travel one way and rectilinearly, supposedly, but because that's what ray reversibility says. But they say, but if you're going to incorporate warp space from space-time, from general relativity, then you have a curvature. Okay, so the little marbles are rolling down this incline because remember, the moon rolls around the Earth because space is warped around the Earth. Just like both of them roll around the sun because
whatever that means.
Because space is warped by the sun. Okay, that's the explanation. And so if the moon
You're taking things too literally. These are just metaphors.
If the moon is rolling around the Earth because the Earth is like a roulette, bent space, the photons are rolling around that space as well. They don't travel straight. They also according to general relativity, not that I'm inventing this, but the photons roll around space. Remember, how do the photons from a star that's behind the sun come to our eyes when there's an eclipse? They roll around the sun through the warp space caused by the sun, right? So the photons roll around warp space. We have to factor all this stuff in there, okay? Remember all this, okay? Photon beads follow the curvature of warp space. And so it's the theory that they put forth. They say gazillions of photon beads go out and only a handful come back, okay? Fine. What is the issue here? The issue is, here's the round trip.
You drew this?
Yeah, so here we have the photons going from Earth to the moon. The moon moved and so did the Earth, and then they come back. Okay, this is what they're saying. I drew too many coming back, okay? It should have been gazillions going out and a handful coming back, okay? But we have warp space. How did they hit the retroreflector with warp space? Not only do they have to shoot in front, but they have to shoot in such a way
that they catch them on the way back.
No, not only that, they have to factor the warp space. And the question is, how warped is space from Earth to the moon? I mean, do they have that calculation?
Well, to first understand this, the first step would be, without warp space, is this akin to throwing a ball against a wall so that you catch it again?
Yeah, but see,
like you're in between,
but that's wrong. That's wrong. No? See, what you got to do is you got to think of it as a toboggan. The slide at the park. It's curved, right, more or less. Okay, so you're rolling the ball along a curve, right? And the moon is moving also sideways.
Yeah.
So not only is it rolling, how are you going to calculate where you're going to hit the moon if you've got this curvature of space-time first? You know the little marbles are going to roll down there. Then the moon is going to move. The Earth is going to move as well. So you're going to get them back through the same curvature, right? Good luck with all that. I think it's overly complicated. It involves concepts which are reified, like space-time. It involves zero-dimensional photons.
But they don't do any of that.
Yeah, but I know, but they
aim and shoot.
Exactly, and if they do that, that means there is no warp space. And if they shoot it in front, remember...
in front, they just nuke the area with light, don't they?
Not only that, but it's important to note. See, I made a little video there showing that the moon is going to be over here. Remember, we're only talking about maybe 70 kilometers. So they don't have to shoot out in the middle of space like I showed in my picture. I just exaggerated that. The point is, they have to shoot in front where the moon is going to be in 1 second, which is 70 kilometers down the road, maybe. Okay, so they don't have to point at the crater. They would have to point where the crater is going to be.
Yeah, but 1 second isn't that much.
But it's 70 kilometers.
Yeah, exactly. That's not much.
But 70 kilometers means you can't point to the crater. They're saying they're pointing at the crater.
Yeah, but
how can you point at the crater if the crater's no longer there? That's my point.
But how fast is it going?
1 kilometer, and the Earth moved 30 kilometers in that 1 second. So the Earth is moving, the moon is moving, and they're saying they're going to shoot that laser, where the moon is going to be in 1 second, which is going to be down the road. Obviously, the Earth is also going to move. We're talking about 2.5 seconds, so you're talking about 750,000 kilometers. Wait a minute, is that right? 300,000, 750,000 kilometers in round trip for the photon.
Yeah.
Okay, and so where are you going to shoot your beam at? Are you going to shoot it at the crater? You can't, because the crater is no longer there. The crater already moved.
Is it though? It's just 1 second though.
You're talking about 70 kilometers. That means where are you focusing? If everything stood still, you say, okay, I focus on the crater, and I'm there. But if light takes just to see it, forget about the laser, just to see the moon, just to see the crater. It took 1 second to reach it. The moon is no longer there.
But it's not no longer there. It's just shifted by 1 second, which is
so where are you going to shoot this telescope? Just a telescope. Forget about the laser.
Yeah, let's just keep the Earth still for now.
Yeah, and
we'll move the moon 1 second. That's negligible.
That's 1 kilometer away. But
we're talking about a 70-kilometer area. So
yeah, but remember, the Earth is moving 30 kilometers, and it's also moving around.
Yeah,
it's not moving in a straight line.
Not without the Earth.
Yeah, but
just to hit the mirror, is the 1 second is negligible. Can we agree on that? Assuming the Earth stood still and the moon was going.
1 kilometer.
1 kilometer is all we're talking about. We're
but
talking
the point is, where are you going to shoot the laser?
You're pretty much there, because it's 70 kilometers. If your circle that you're going to hit on the moon is 70 kilometers, and it just moves 1, It's basically the same thing.
Yeah, it's not the same thing. It's that again, what they do. That's why they have to shoot a rest, or they shoot a big region because they say somewhere in there.
Yeah. That's a big problem with this whole thing, where it's that you can't really talk about precise measurements because they're basically just nuking the area until they hit something.
My argument is that the two assumptions are wrong. That light consists of particles, discrete particles, little balls, and that space-time is warped.
Yeah.
It kills those two, quantum mechanics and general relativity, in one shot.
Or else they would have to factor those in.
Because
which they don't.
Because well, they do to some degree, but it's. I mean, what is the curvature of space? I mean, have they figured out how much curvature is required for the moon to go around? And if you have to calculate that, you know that the Earth has to be weighing the canvas very deep for the moon not to fly away, for it to find this wall. And along that same curvature, the photons are going to be falling in there. And so you get this curvature, very pronounced curvature. That's not what they do. They shoot it directly at the moon. Are they when they point at the crater? Forget about the retroreflector. When they point at the crater, are they pointing downwards to where the? I mean, what is this? No, they're pointing directly. It's a straight line. Essentially, it's a straight line. It should not be a straight line if space is warped.
It's like bowling by throwing the ball straight at the pins instead of along the floor.
Yeah, imagine you're bowling. Imagine you're bowling and the field is curved.
Yeah, but they just ignore that and they just throw it straight at the pins.
They're throwing it straight at the pins, but if relativity is correct, it should be going. Your bowling ball should be
dipping first and then hitting. So aren't they essentially rolling these marbles up because?
They're not. They're shooting directly at the moon.
I know,
and how are you going to explain that except that you are instantaneously, essentially, right, from our point of view, 300,000 kilometers away, but still it's essentially a straight line. Because if there is curvature of space-time, that thing should be a very deep curve. Not only a curvature, it's very deep for the moon not to fly away. See, and they don't explain that. They treat all these things separately, and it's like nobody puts them together. That's my point. Okay, anyways, here's some more issues here. Fellow says they represent the paths of electron. He's saying that the magnetic lines of force are electrons. That's another.
Wait.
Yeah.
Wait, one ring is an electron going around, or what?
No. He's saying the lines of force there that you see in the magnet. First, let's look at the magnet on the top. Okay. He's saying that those lines of force are electrons.
But is it a chain of electrons or one electron going around?
Well, I'm assuming he's saying it's a chain of electrons. He's saying there's gazillions of electrons moving in those lines. That those lines are electrons. That's what he's saying essentially. So they represent the paths of electrons in different circumstances. You can build an apparatus, he doesn't explain much more than that. He just says you can build an apparatus using the read sensor out of a hard drive to detect the individual electrons moving along these magnetic field lines. And I'm saying that people who still do physics with particles, they have to be mentally retarded. Okay, they have to be mentally retarded because we have not been able to explain anything in the last 10,000 years with particles. The universe doesn't work with particles, with discrete particles. You can't explain it. You can't explain how two particles which are separated, how do they do push? How do they do pull?
Well, push is easy.
No, they're separated.
Oh, I see what you mean.
Please do push or pull. Right there. Explain that. Just two particles.
You got the string here.
With that you can do that. Here you have two particles. We have space in between, nothing in between. And you want to put gazillions of particles, go ahead and do it. But we just need two of them. How does this particle affect this one? From a distance, whether push or pull. That's all you got to explain. The day you can explain that, no math, no equation, we don't need any of that. We just need a physical mechanism. How does this particle affect this particle if they're not even touching each other? If all particles in the universe are isolated, how does one particle affect another? So no, you cannot explain push or pull, the only two forces we're aware of, except in quantum they have four forces. And then, there you have your atom. If the electron, like this individual says, is a discrete particle, explain your atom. Show me your atom. Show me how that electron doesn't fly away. What keeps it bound to the proton? Again,
and why does it go in that specific?
It's the same issue.
Why does it go in that specific? What do you call it?
It's the orbital, energy level.
Trajectory.
Yeah, they call them energy levels, orbitals.
But assuming that each one of these lines of force, each ring line of force, were one electron, going around, why does the electron follow that specific?
And the same thing with the electron on the bottom. Why does it follow? I mean, you don't have to even have an orbit because the current version is that the electron jumps anywhere within that yellow region.
Yeah.
Great, fine.
It's not going around.
I just want to know why that electron, what stops it from flying away spontaneously or from falling to the nucleus. That's what you got to explain. And the same thing what Anja said about the magnet. If it's electrons going through those lines, don't tell me how to detect them. Tell me how, visualize for me, make a movie of how that electron goes around and why it does that. Is it tied somehow to the magnet with a little string?
Yeah.
Is that why it goes around?
It's going through a very specific orbit.
Yeah. You got to explain why it does that. Yeah. Don't tell me that it does. We know that it does. The question is how.
Well, we don't know it does.
Well, I mean, we'll concede.
We assume that it does.
We'll concede what this guy says.
We assume that it does, but
electron
then why
balls.
would it?
Yeah, why would it? That's all you got to explain. Once you get that,
why not further? Why not closer?
Other fellow also shows our dear.
Made of math.
Yeah, we have.
Math is real. We are made of math.
Yeah, Sabine Hassenfelder, and she says, math is real. We are made of math. And you go into that video. She just put it up the other day, and she says the following: the things that I thought was important. It's got to do with the word existence, and that's where we have the problem. What is real? And she addressed that issue essentially. And she says, in physics, something is real because it's a good explanation for our observations. But remember, what did she say? It's a good explanation. She uses the word explanation. She continues, we can't actually see elementary particles with our eyes. We say they are real because certain mathematical structures describe our observations. This lady doesn't know the difference between an explanation and a description. She just uses these words interchangeably. And no, in all of mathematics, you will not find a single explanation. All you'll find is descriptions. Math can only describe. But she uses the word explanation when it's very clear that mathematical physics cannot explain anything involving invisible entities. It doesn't have a rational explanation for anything. And she says, if you see 3 apples, 3 describes what you see. Yeah, therefore it's real.
The 3 is real?
Yeah, that's what she's saying. It's real because 3 is a number, is the word, the number, the whatever that we use to describe.
She's saying the word, the concept 3 is real.
Yeah, and she says, if that's the notion of reality that you don't want to use, I challenge you to come up with a different notion that is consistent and agrees with how most people use the word.
What?
We don't care how people use the word. We don't care because science is not about voting and saying, I like this definition. We don't care if all of humanity votes for the same definition or for the flat earth.
Depends on
Mother Nature laughs at humans that are wrong.
Well, no, it's not about that. It's how you want to use the word, isn't it?
No,
she's talking about the notion of reality. If you use the word reality for one way and I use it for another.
No, in science we don't have different notions of reality. The way we do it, we get inside the ring, we fight, and only one man remains standing.
That doesn't make sense.
Yeah, we cannot have
two different. Define our words.
You define your word, but you got to defend your definition. If someone shoots your definition and tears it to pieces, you can say, "Well, I'm going to use it anyways." Yeah, the word object. People say it's see and touch. That's the criterion. No, we can easily demonstrate that an object is not that which you can see and touch. That's not an object, not for the purposes of physics, of science. In ordinary speech, that's an object, not in science. In science, you got to defend that definition, and I'm saying you can't see or touch the table that's on the other side of this planet. The Chinese table over there, I can't see or touch it. So is that table not an object? Is the word table, doesn't it refer to an object? So clearly the criterion is not see and touch, and he who brings the see-touch criterion is I don't care if everybody votes for it. It doesn't make it true. Because of that, Mother Nature laughs at that person. No, an object is that which has shape. All objects have shape. It's a universal property. Not all objects can be touched. Not all objects can be seen. Now we have a definition we can use in science. You don't like my definition? It's not you go ahead and do your thing. No. Get inside the ring and fight if you want to do science. Defend your definition and attack mine. That's the way it is.
I like how she sees 3 apples and she says the apples are real and the 3 is real. What?
Yeah, the 3 is real. Yeah.
Sorry, you lost me on that second one.
Yeah, so this is the way we define it in science. We say exist physical presence. An object is that which has shape, and exist is an object that has location. If it doesn't have location, it's an object, yes, but that doesn't exist. More or less like that fellow in the center there. You know, he's an object, but he doesn't exist.